escaping the boot2 sector. You only get 252 bytes to play with in boot2. That's obviously going to be quite inadequate for most purposes, and we need to somehow break out of the boot2 sector into the main flash. I reconstituted the boot2 sector from the Raspberry Pi SDK. So let me just have a look at that. I pulled it out into just one bit of code. Let's have a look. I would rather have written it in C, but I'm going to stick with what the Raspberry Pi Foundation came up with because I don't know what half of this stuff does. Pull up the power, I don't know. The main bit I want to look at is vector into flash. This here. You run through all the above code and you eventually get into this vector into flash function here. Now you load R0 with zip base plus 100 hex offset. This gives it the value here. So this value is where your vector table is stored in flash. Your vector table consists of the top of the stack in memory and then a bunch of interrupt request addresses. The first one is the reset vector. That's going to be the most important one for us, and it's the only one I'm going to implement plus the stack. So R0 points to where the vector table is. Now, how do you tell the ARM processor where that vector table is? Well, you set R1 with this address here. It's address E000ED08. Where did that come from? It comes from the ARM architecture reference manual. And you can see the VTOR table, VTOR register here at address I just mentioned. It is the vector table offset register. That's the one we want. We store the vector table address in the vector table register. And we execute this command. We load register R0 with the location of the stack pointer. Remember, the stack pointer is the first address in the vector table, and we also load R1 with the reset function address. In here, MSR MSP R0. So now we set the top of the stack. This is we're actually setting stuff. We're actually set the top of the stack with the contents of register R0. Right, so now we have the top of the stack properly. And then we BX R1, so we jump to the reset function. Right, so now we should have set up the vector table and ready to jump into our main function. Let me just have a look at the linker script. See how that's done. I think that's quite important. So we need to go down here. Right. Here we see the flash is located at address 10000000, and the RAM is at address 2000, etc. And it's of length 256k. We'll get back to that. This is the linker. That's not interesting. The boot2 section is where our boot2 code goes, and here we do an assertion that the boot2 is of length 256. Now I've altered the linker a little bit in that I've split out the ISR vector. These are the vectors of interrupt vectors, including the stack pointer. So I've called a section ISR vector. We'll look at that in the main code, and the rest of all this is mostly the same, except that I've removed these vectors because I moved it above
and I changed the name.
So there's a few sectors going on here. Let's look at main to see where things are. What should we look at? The delay function is as before. And now here I'm setting up my ISR vector of interrupts. Now, according to the ARM reference manual documentation, the first value you've got to put into the ISR vector is the top of the stack. If you recall, the top of the beginning of RAM is in 20000. There's 256k of RAM available, which comes out at a hex value of 42000. So you add those together to give the very end of RAM. Then I put in the main function.
That's our reset vector.
You may want to call it something like the reset handler, but I just called it main. And here's main. So main does what we did before, pretty much, in the boot2 section itself. I've done a little bit of abstraction out of here. This section is the same as in the previous video, and now I had created some functions called GPIO out, GPIO set, delay as before, GPIO clear, and delay. So GPIO set is basically just what we had before in the previous video. You set GPIO SIO, GPIO out set, and you set the bit 1 displayed to the left by the GPIO number. GPIO clear is similar as before. GPIO is now a little bit more abstract. You need to work, instead of just setting a hard coding GPIO register and work from a base, you need an offset of 4, because that's where the control registers are, as opposed to the status registers, and each GPIO occupies 2 registers, the status and control. So I multiply that by the GPIO number. So you can put a register number, and then you set that equal to value 5, which, as you may recall, means I want it as a standard GPIO. Then this is pretty much as before. We set the GPIO as an output register. That's that. Let's just have a quick look at boot2.ld, because I changed this a bit. from previously. Instead of flash, I called it boot2 just to distinguish from just calling it flash. The address is the same as flash, and I'll put the length to 256 bytes. Now in the boot2 section, I have a main. This is not the main that I just showed you. This is the main of the boot2 loader itself. So you load a bunch of stuff in for boot2 that I showed previously, and I now have a fill region just to make things neater. So what's in the bootloader may not be 252 bytes. So what I do is I set a fill value up until the end of the boot of 256 minus 4, and then I just output 4 bytes. This just pads out my object file to 256 bytes. We still need to do the checksumming as I showed in the previous video. Let me show you the make file. I've tidied it up since last time. And essentially put everything in a oneer. So I create an S file, an assembly file called boot2-gen.s, which I compile from boot2.0, and this LD is the linker script. I use the boot2.ld that I showed before, and I create a boot2.elf. Right, so we need to do the checksumming, so I just dump that to a raw binary called boot2.bin, and I do the checksum, which has been slightly changed. It will set the checksum properly.
I won't bother showing you the checksum.py function, I don't think.
This time I do create a UF2 file. Remember last time I used Pico tool to upload to the flash, but here I decided to go for a vanilla UF2 file. What else?
And I'll just point out the object files we need to compile together is main.o from main.c and boot2-gen.o, which comes from boot2.o augmented. So let's make the project. Right. Let's do a hex dump of boot2.bin, see what we get. And we see a value of 7A4E B274, so we know that the checksum's been done. And what I will do is I will have a look at the disassembled binaries app.dis. So we go through here. So there's the address at start of flash, and this is the boot2 bootloader. Now these values correspond with what's in boot2.bin. You'll notice that the decompiling of it looks completely wrong. That's because it's using ARM rather than thumb, but it is correct. but it's just decompiled it wrong. But that's okay, that's not a problem. It's actually correct. Now we have the ISR vector, which is stored at this address 10000100 in hex with our IOQs. And if we look here, top of the stack is the first value, and this is the address of main. Now again, we ignore this decompilation, it doesn't mean anything, and it says invalid instruction. Well, yeah, because it doesn't decompile to valid thumb code. It's an address. So let's have a look down here for address 100001BD. That should correspond to main. So let's have a look at main. And well, it almost seems correct. It's 100001BC rather than 1BD. What's that about? Well, it's got to do with the fact that thumb mode works differently to normal ARM mode. So when the processor jumps to this main function, it's got to know that what it's going to execute here is thumb code and not normal ARM code. How does it do that? It adds 1 to the address. So in fact, it will execute from this address, but the extra low significant bit of 1 tells it that it's got to decode everything it sees as thumb. So this is what the decode of main looks like. And this delay and GPIO, this is how it's decompiled, and GPIO set and GPIO clear. So I think that's all I wanted to show for you today. I hope you found that useful. Thanks very much for watching, and bye.